Organic chemistry.
All right, so we're going to do a bunch of multi-step problems. So let's begin with this example. So before we dive into the mechanism, let's list out the factors just so we know which type of mechanism we should follow. So if chlorine is our leaving group, it's attached to our alpha carbon, which means it's also attached to beta 1 as well as the beta 2 carbon. So because this leaving group is attached to 2 beta carbons, that means this is a secondary alkyl halide or electrophile. MEOH is a weak nucleophile as well as a weak base, just because it cannot separate to form any charges. And then lastly, this doesn't have a specific solvent written underneath the arrow, so we can assume that methanol can also be used as its solvent, which means it's also polar protic. So if you looked at these factors on the chart, we'll find that if you have a secondary electrophile slash alkyl halide with both a weak nucleophile and weak base, that means this proceeds through SN1 slash E1 mechanism. And the first step for both of these mechanisms is the same, where we have to form a carbocation. So now we can dive into the mechanism now that we know that it proceeds via both SN1 and E1. And that means that the first step is that our leaving group has to leave to form a carbocation. So that first arrow starts from the middle of the bond where the leaving group is connected to the alpha carbon. And that arrow just goes to form a new lone pair onto chlorine. Now that we have made it to this carbocation intermediate, now our pathway can basically diverge into two different paths just because it's proceeding through both SN1 and E1. So let's just first draw the SN1 pathway, but eventually we'll get to the E1 as well. But if we're following the SN1 pathway first, and I'll just write it up above here, next step in the SN1 pathway, once we form the carbocation, is our weak nucleophile methanol can attack the carbocation from both faces, just because remember the carbocations are trigonal planar, therefore they're flat, which means that our nucleophile can attack from both the front and the back of the planar carbocation. And don't forget to draw in the lone pair in oxygen as well as the plus charge, the formal +1 charge on oxygen. And because we want our overall product to be neutral, but currently we have a charge on that oxygen. Remember the third step or the second part to part 2 of SN1 is that the leaving group, which was chlorine, comes back in is going to deprotonate this extra hydrogen. So Cl- grabs the hydrogen, and then the bond in between oxygen and hydrogen forms a new lone pair on that O. So the first product of this SN1 reaction, or of this multi-step problem, is this product, which will be a racemic mixture of products. And remember, the definition of a racemic mixture is you have 50% of R and 50% of S. We could have specified stereochemistry at this point, but if you do decide to do that, you have to draw both the wedged bond as well as the dash bond to ensure that you're showing the racemic mixture of products. But just drawing it on an in-plane bond and labeling it as a racemic mixture is totally fine. So this is one of the products of this reaction. So now let's go back to our carbocation intermediate and then discuss what the E1 pathway would look like. Okay, so if we're taking a look at the E1 pathway, now we're going to use methanol as a weak base. So we have to take a look at each side of the carbocation, because remember, this could be labeled as our alpha carbon, and that would make each side of the alpha carbon beta carbons. So if we also wanted to label or draw in those hydrogens connected to the beta carbons, we can do that as well. So beta 1 has 1 hydrogen and beta 2 has 2 hydrogens. Remember, for E1 reactions, they exclusively follow Zaitsev's rule, which means that our base should or wants to deprotonate a beta hydrogen that's connected to the beta carbon with a smaller or lower number of H's. So looking at our current molecule, beta 1 has 1 hydrogen, beta 2 has 2 hydrogens. So we're going to use our weak base, methanol, to deprotonate from the beta 1 carbon. And also feel free to draw out the structure of the base if that helps you. So one of the lone pairs from oxygen of methanol is going to deprotonate that hydrogen, and then the bond connecting hydrogen to the beta 1 carbon, the bond is going to go in between the bond between alpha and beta 1 carbon, and then that's it. We just have 2 arrows to draw just because our leaving group, chlorine, already left. And remember that E1 reactions are also a 2-step reaction as well. So from here, we form our alkene. At this position. And now we can continue on with the multi-step synthesis, because the second part of this multi-step synthesis is using BH3 as well as THF. So we weren't able to use BH3 with the SN1 product just because we didn't have an alkene formed in that product. So we're only going to proceed with the multi-step synthesis using the E1 pathway, just because it does form that alkene that gives us more of a handle to do more reactions onto it. So because in this next step we're using BH3, I'm going to draw out the structure of BH3 just so we can show that hydrogen boron bond, just like that. And then remember, the arrows for hydroboration is that we're going to draw our first arrow from the alkene, and it's going to go towards boron. And then the second arrow that we're going to draw is going to go from the hydrogen-boron bond, and it's going to attack the more substituted carbon of the alkene. So just those 2 arrows. And from here, we're going to form our first intermediate. And remember that this process happens such that the hydrogen and BH2 groups can add on to the alkene via syn addition, aka they're both on the same types of bonds. I'm just going to draw them as both on wedges, but know that this also could be drawn such that they're both drawn on dashes as well. And because we're drawing the hydrogen of BH2 on a wedged bond, this methyl group that was already connected to the alkene is going to be on a dashed bond. Now from here, the next step of hydroboration-oxidation is we're going to add 2 more moles of our original alkene. So we're just going to redraw that up above these 2 arrows. And then essentially after this step, we're drawing basically the same intermediate, but instead of BH2, it's going to be Br2. Where R in this case is, I'll write it down below, R equals the cyclopentane with that wedged hydrogen as well as a dashed methyl group. And then from here, just the third step of the reaction, where we are reacting it with hydrogen peroxide, H2O2, NaOH, as well as water. And remember, you do not need to know the mechanism of this third step or the second step of hydroboration-oxidation. But essentially, what's going to happen when we add these three reagents is that we change Br2 into an alcohol group. And from there, we get our final product. And remember, you also form the enantiomer of this product as well. So if we were comparing this product with what we got from the SN1 reaction, going back to the type of alkene that we formed, after we proceeded through E1, we can see that the type of alkene that we formed after E1 was a tri-substituted alkene, which means that it is going to be a major product and the SN1 reaction product will be the minor. So because this is a tri-substituted product, and remember, anytime you form either a tri or tetra-substituted alkene after proceeding through E1, that means the E1 product is going to be the major, SN1 product is going to be the minor. So because this was our major product, as we proceeded through hydroboration-oxidation, we can label this as our major product. And then the SN1 product that we formed previously would be our minor product. So for this problem, if we broke down what each of the steps do, that will give us a game plan as to how we can complete this multi-step synthesis. So H2SO4 in heat is only exclusively used to form an E1 product. So we know for this first step, it's going to proceed through an E1 mechanism. And then O3 and DMS, those two reagents are paired together, and this proceeds through ozonolysis. So we know that after we form our alkene, after the E1 mechanism, then we know to proceed through ozonolysis, which you do not need to know the mechanism for. You just have to remember that this forms two carbonyls. All right, so now let's try the mechanism. So in this multi-step synthesis, the first step is that we're reacting this alcohol group with H2SO4 in heat. This means that the reaction or the mechanism that we're going to draw proceeds via E1. And H2SO4 in heat is the only reactant that proceeds exclusively through E1. You are not going to get any SN1 side products. It's only going to proceed through E1. So let's draw the mechanism for this reaction. First step is that one of the lone pairs on oxygen of the alcohol group is going to grab one of the hydrogens from H2SO4. Then the next step is the bond in between H and O is just going to form a lone pair on that oxygen. So what you create is water as your leaving group, which is a much better leaving group than alcohol. Now, because this is an E1 mechanism, the first step of E1 is that the leaving group has to leave to form a carbocation. So that's just going to pop off, and the bond is going to form a new lone pair on water. Now from here, HSO4- is going to come back and act as a base. And remember, E1 always follows Zaitsev's rule. So if we took a look at the hydrogens connected to each side of this carbocation, because this is technically our alpha carbon, there are 2 H's to the right, 3 H's to the left. So between beta 1, which we can label the left side as beta 1 and this side is beta 2, HSO4- will prefer to deprotonate from beta 2, which is the beta carbon with less H's. That's Zaitsev's rule. So from here, HSO4- will deprotonate a hydrogen. The bond will go in between the alpha and beta carbons, and those are the only 2 arrows you need to draw. So from here, you form that alkene. And then now, because we formed our alkene product, the E1 mechanism is over, and then we can proceed to the next step of the multi-step synthesis. So from here, the next step is that this is going to react with NaOH and DMSO. Oh, sorry. Next step, it's going to react with O3 and DMS. And remember, you do not need to know the mechanism for ozonolysis. The only thing that you need to remember is that ozonolysis acts like a pair of scissors. Wherever your alkene is located, you're just going to cut that in half and form your 2 carbonyls. In case that's still confusing, we can number our carbons just so we can see where everything is being placed. And I'm just going to draw the products down here just for more space. So our alkene is currently located in between C2 and C3. So this is where we're going to cut our molecule in half because we do have a linear alkene. So if we were to number our carbons, the first product would have carbons 1 and 2. The second product would have carbons 3 and 4. So you can see that the carbonyl, or the oxygens that are part of the carbonyls, literally attached to C2, which was the left side of the alkene, and C3, which was the right side of the alkene. And from here, these would be your products. All right, so for this reaction, now let's break down what each of these reagents are going to do so we have a game plan as to how we should proceed with this mechanism. So HBr with an alcohol group does not mean hydrohalogenation because you need an alkene to do that, but rather this means that we're going to do an alcohol displacement reaction. When we add NaOH in DMSO, this would proceed through an E2 mechanism. And then H2 and palladium is a catalytic hydrogenation reaction, which means we're going to remove any alkenes and change them to alkanes. So let's get started. Okay, so for this reaction, we're proceeding through an alcohol displacement. So you know 2 different reactions that you could proceed through using HBr. Either HBr can proceed through hydrohalogenation, but that reaction requires that you have an alkene. Or you could use HBr to undergo an alcohol displacement reaction, which in this case, because we are starting with an alcohol group, that means we're going to proceed through that reaction as opposed to hydrohalogenation. So the first step of displacing this alcohol is that we have to turn it into a good leaving group. So the first thing that's going to happen is that one of the lone pairs from alcohol is going to grab this hydrogen, and the bond is going to form a new lone pair on bromine. This forms water, which is a much better leaving group than alcohol. And then once you have that good leaving group, then an SN2 reaction can happen where Br- comes back and attacks the alpha carbon, and then our leaving group can pop off and leave. So this allows bromine to attach, which is a much better leaving group than OH was. So now from here, we're going to move on to the second step of the reaction, and that is we're going to react it with NaOH as well as DMSO. So before we go into any arrow drawing, let's figure out what type of mechanism we should follow based off of the electrophile and nucleophile/base that we currently have. So if bromine is our leaving group, this is attached to an alpha carbon. We got beta 1 and beta 2. So that means that this is a secondary alkyl halide or electrophile. NaOH is a strong nucleophile as well as a strong base. And DMSO is a polar aprotic solvent. So because we have these factors, if you take a look at the chart, this will point to that this is an E2 mechanism. So remember, for E2 reactions, then we have to take a look at the size of our strong base to see which rule we should follow. So E2 reactions, now let's take a look at the base. If we were to separate it into Na plus, OH minus, OH is a small, strong base, so that means we're going to follow Zaitsev's rule. In this problem, it's not as important to determine which rule to follow, just because it is a symmetrical molecule. But just in general, anytime you're looking at an E2 mechanism, make sure to look at the size of the base so you know you're following the correct rule. So in this case, it doesn't matter which hydrogen we use to deprotonate. So let's just say let's deprotonate one of these hydrogens using OH minus. So it's an E2 mechanism, so this all happens in one step. The base deprotonates a beta hydrogen, the bond goes in between the alpha and beta carbons, and then our leaving group leaves. So in total, 3 arrows. So this will form an alkene at this position, and then we can go on to the third step. So now we're reacting it with H2 gas and palladium as our metal catalyst. And remember, you do not need to know the mechanism of this reaction. All this does is it changes the alkene and adds these 2 hydrogens, syn addition across the alkene, and you get your alkane. So if we break down the steps of this multi-step synthesis, well, the first step uses tosyl chloride and pyridine. So we know that this is a way to change alcohol into OTS, which is a good leaving group. Second step, we're using KOTBU and DMF. So remember, potassium tert butoxide is a strong, bulky base. So we know that this proceeds through an E2 mechanism, and we're going to follow Hoffman's rule. And then steps 3 and 4 mean that we're going to perform ozonolysis. So we know that our final product should have 2 carbonyls. Now let's get started. So the first step of this multi-step synthesis is that we're going to use tosyl chloride and pyridine to change this bad leaving group, this alcohol group, into a good leaving group. So the first step is that one of the lone pairs from oxygen of the alcohol group is going to attack the sulfur atom of this tosyl chloride. And remember, this whole chunk is considered to be a tosyl group other than the Cl. So a lone pair from oxygen is going to attack sulfur. Chlorine pops off. And this forms the oxygen is now attached to both a TsCl group, but the hydrogen that was originally bonded to the alcohol is still there. So because of that, we're going to bring in pyridine, which is a base. And the lone pairs connected to nitrogen is going to deprotonate that extra hydrogen. And from here, we form just the OTOS group. Now, the next step of this reaction is that this OTS group is going to react with KOTBU and DMF. So the reagent kind of gives it away as to what reaction we should proceed by, because potassium tert butoxide is a strong, bulky base, which tells us that this is going to be an E2 mechanism, but we're going to follow Hofmann's rule. So remember, Hofmann's rule means we're going to deprotonate a beta hydrogen that's connected to a beta carbon with more H's. So going back to our intermediate, if OTS is our good leaving group, that means it's attached to an alpha carbon, and we have beta 1 and beta 2. So if we take a look at the hydrogens connected to there, so beta 1 has 2 H's, and beta 2 has 3 H's connected to it. So for following Hofmann's rule, we're going to want to deprotonate a hydrogen from the beta 2 carbon. And I'm just going to draw the base closer to the hydrogens. So our strong bulky base is going to deprotonate a hydrogen connected to beta 2. The bond is going to go in between the alpha and beta carbons, and then OTS, our leaving group, is going to leave. So in total, 3 arrows need to be drawn, and since it's an E2 mechanism, all of this is happening at the same time. So the product that we would get would be this alkene. And then the final step of this multi-step synthesis is our alkene is going to react with O3 and DMS. So adding KOTBU was the second step. So this will be the third and fourth steps. And you don't need to know the mechanism for this ozonolysis. We just have to remember that this acts as a pair of scissors and it'll cut our alkene in half. So let's number it again. So the first product that we will form will have carbons 4, 3, and 2. And then the second product that will form will have carbon 1. And you can draw in the hydrogens too, if that helps you visualize it better. So that will just have C1. And with that, those are our 2 products. So in this multi-step synthesis, the first step is we're using PBr3. So remember that this is a reagent that we use to change alcohol into a good leaving group. So in this case, we're changing alcohol into a bromine group, which is a good leaving group. The second step is we're going to use sodium ethoxide, or NaOET, and acetone. So from here, it depends on what type of alpha carbon, as well as how many betas are connected to it. So this could proceed either through E2 or SN2. So we'll take a look after we change it to bromine to see which mechanism to proceed. But because the third step is H2 and palladium, so it's catalytic hydrogenation, this tells me that in order for this reaction to occur, most likely this is going to proceed through the E2 mechanism just because that does form that alkene. And then in the third step, the alkene will be reduced to produce an alkane. So let's get started on this mechanism. So in this first step of this multi-step synthesis, we're changing the alcohol group into a better leaving group using PBr3. So the first step of this alcohol displacement mechanism is one of the lone pairs from oxygen is going to attack the phosphorus atom, and then one of these bromine groups are going to leave. It doesn't matter which one, either of the three work. So from here, we're going to form our intermediate. Where oxygen is connected to both the hydrogen as well as PBr2. And then from here, all that's going to happen is that bromine, the Br minus that popped off, is going to come back and it's going to attack the alpha carbon of our now good bulky leaving group. So now we have this intermediate, and now we can move on with our multi-step synthesis, and the next reagent it's going to react with is NaOET and acetone. So if we were to list the factors of this problem, bromine is connected to the alpha carbon and it's got beta 1 as well as beta 2. So that means that this is a secondary alkyl halide. NaOET is a strong base and it's also a strong nucleophile. Acetone is a polar aprotic solvent. So if you take a look at the chart, all of these factors would point to that this is an E2 mechanism. So now we have to take a look at the size of our base. So if we were to separate it, we have Na plus and OET minus. Ethyl is considered to be a small group. So because it's a strong small base, that means we're going to follow Zaitsev's rule. So remember, Zaitsev's rule means we're going to deprotonate a beta hydrogen from the beta carbon with less H's. So between beta 1 and beta 2, hopefully by now you can start to visualize how many hydrogens are located on them without having to draw them all out. So because of this, beta 2 has less hydrogens connected to it than beta 1, so we're going to deprotonate a hydrogen from that position. So our base, OET minus, is going to deprotonate a hydrogen from beta 2. The bond will form the alkene in between the alpha and beta 2 carbons, and our leaving group will pop off. So from here, we form our alkene intermediate for this step. And then lastly, we're just going to react it with hydrogen gas, as well as palladium as our metal catalyst. And from here, we get our final product.